All right, everybody, let's get started. It's been a while since we've been together, so it's welcome back. I trust everybody's 5-day break from CE 312 was fruitful, and then everybody got some hopefully rest and relaxation, and hopefully too many of your faculty didn't go, "Ooh, you have like a long weekend. That means I can give you a bunch of work." You know, some of you are like, "Yeah, that happened."
A little bit.
Okay. I don't think that the project was, did it fit into that category? I hope it didn't. No. I hope it didn't. Okay. All right, so a couple of logistical items. We don't have an exam in here for a little while, so I didn't put like a, you know, oh, here's when the exam is. Although it is, I mean, it's going to be relatively soon. After this topic on deflection on beams and frames is when our exam is. And so we're going to be having 5 lectures on that, and then you know, exam, review, exam, all that. So it's coming up relatively soon. A couple housekeeping items. The attendance grades are up to date on Blackboard. Everything on terms of homework up through 5.5 is graded. 5.6 is still being graded. You don't have any homework due today because you submitted your Project 1 submittal. I'm not assigning any homework today because you have homework 5.7 due on Wednesday, okay? Everybody good with that? Okay, so the only thing that was due today was the first submittal for your project. Give me about a week or so to grade that. Usually I can get those graded pretty quickly. There are a few things that I'm looking for in your submission, and as long as your submission adheres to that, you're good to go. Most often, if you develop 3 trusses and you picked truss 3, 99 times out of 100, I'm going to say that's fine, go ahead with truss 3. The only time I'll ever say that you can't go with truss 3 is that if it violates a constraint for the problem that you didn't check, like if one of the members is longer than the maximum length, or if there isn't a joint that span or something like that. But by and large, other than that, I'm going to adhere to that. Okay. The only other thing I wanted to mention before we go down the rabbit hole of our topic today, which is deflections, is mast hand. Okay. Later on this semester, actually right after exam 2 land, we're going to be spending a few days analyzing structures using software. And specifically, the software package that we're going to use is masthand 2. I like masthand 2 for a couple of reasons. It's pretty simple to use. The price is right because it's free, and it is both Windows and Mac friendly. And it is surprisingly powerful. Like, it is a very simple interface. The usage of masthand is really like simplistic, but what it can do, it packs a punch because it can do a lot of really advanced analyses really easily. If you go to Blackboard, so I have here Blackboard for the class, and I have it set up, you know, sort of the way that you can see it in student preview. If you go to lecture notes and supplements, you'll see here topic 7. It says structural analysis using masthand 2. And if you click this, it will take you to a link for where you can download masthand and some instructions on how to do that. Also, if you have a Mac, you may have to sort of like force your Mac to allow it to install. It'll work on a Mac, but your Mac may think that the app is from an unidentified developer and it might get angry at you. So I put a link on how to get around that. I promise it's fine. I'll say this, there are 2 ways to install masthand in general. Those of you that have MATLAB on your computer and those that don't, masthand is a MATLAB-based program. Doesn't mean you're going to be writing MATLAB code or anything, but it uses MATLAB as the engine for a lot of the calculations. Trust me, you won't be programming any MATLAB in here. And so as a result, I imagine some of you do not have MATLAB installed on your computer because once you were done with Engineering 111 and programming, you sort of conducted an exorcism on your laptop and got MATLAB off of it. Some of you are shaking your head like, yes. I know things. So if you still have, so the point is, if you do still have MATLAB on your computer, the installation I think is just different. So it doesn't matter either way. But there is going to be a homework later. I think it's homework like 6.3 or something, where literally the only thing I want you to do for the homework is install masthand and upload a screenshot of it running on your computer. That's the homework assignment. Because after exam 2, we are going to do masthand analyses together in this class. So I want you bringing your laptop with masthand installed, ready to go. Sound good? Okay. Let's see. Yeah, I'm still recording. I thought I heard something with the computer. All right. Okay, everybody get the code? He didn't get the code. He did not get the code because he walked in a couple minutes late.
Listen,
he's like, I'm wearing this hat. He won't notice. I'm just messing. I'm just messing. I'm just messing. Okay. I'm just playing. All right. Okay. So today what we're going to do is talk about deflections, and I'm going to go ahead and tell you today is going to be a little bit like movie time, whereas we're going to be talking, it's going to be a derivation. And so I just want you to sort of sit back and just sort of absorb what we're going to talk about today. Before I start clicking through the slides, I want to go through a couple of summary bullet points here on the board. And nothing here that's on the board isn't going to be here in the slides. I just want to use this for discussion purposes. Okay, so let's, I don't know, let's just sort of strike a line in the middle of the board just to sort of separate our discussion. Okay, so the first thing I want to talk about is axial deformation. Okay, so this is axial deformation. And this is basically what we dealt with trusses, okay, when we did a truss analysis. Now, if you recall, if I wanted to find the deflection at some point in a truss, okay, at some joint, we would be using the principle of virtual work, right? And remind me, so let's make sure we're all on the same page. So the method of virtual work says that we perform two analyses, right? We perform a real analysis, so we analyze the structure subjected to the loads as they are present on the original problem. And then we conduct a virtual analysis. So remember how the virtual analysis works? You kick all the original loads off the structure, and then you put a single unit load at the point that you're interested in finding the displacement in the displacement's assumed direction. And then if you get a positive answer, that means the assumption's correct. If you get a negative answer, the assumption's incorrect. Everybody with me on that? Everybody remember that? And so the way that you would compute deflection is you would say we're going to sum up the following fractions. We're going to sum up this, this, and this. And this would be how you would compute truss deflection. Am I right? Like that would be how you would do it. Now, I want to show you something before we talk about flexural deformation over here. Over here, we're going to talk about flexural deformation. I'll just do it like that. And this is going to be for beams and frames. Before we do that. Now, this is one way of writing our expression for axial deformation. Okay? I want to show you a potential second way of writing it. Okay? A potential second way of writing it would be to do this. Would be to do that. We'll say 0 to L. First off, some of you are like, come on, Dr. Mike, it's been 5 days. You're breaking out the calculus. My coffee hasn't even kicked in. What are you doing? But we'll get to this here in the slides here in a bit. But what I am proposing with this second way of writing it right here, what I'm saying is this first way of writing our expression assumes that everything is constant, whereas integrating assumes things change. Okay? And to give you some concrete examples of what I'm talking about in terms of things changing, we would need to do a method like this if we had, for example, truss members whose cross-section changed. In other words, when we look at an element in a truss that's 20 foot long, we assume that it has the same area across the entire member. But like, what if the member tapered? What if it went from a really small area to a really big area? If that was the case, we really couldn't assume that area is constant. We would have to take that into account somehow by when we sum up the energy, we would have to integrate. But we've never really had to do that, and to be honest, in most real-world applications, we really don't have that. We don't have truss members whose area changes across the members, so we didn't really talk about that in here because we don't see it in the real world. But that's really not the salient point for the difference between this and this. The real salient point is that the big reason that we didn't integrate is because the forces didn't change. When we analyze a truss and we get that member AB is experiencing 30 kips in compression, it's 30 kips in compression everywhere along the member, right? If here's the truss member, it's 30 kips in compression here, 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 everywhere, right? So because everything is constant, we don't need to take into account integration. The problem is that is not going to be the case over here with beams. How many moment diagrams did we draw where the moment diagram was just constant? That didn't happen, right? Moment diagrams went up, down, curved, linear, they were all over the place. So when we compute deformations for beams, either deflections or some rotation, what we're going to have to do is sum up some integrals, okay? And the form is going to be very similar. Instead of little f big F, it's going to be little m big M, okay? And instead of over EA, it's going to be EI. And that's going to be our expression for virtual work for beams and frames. The process is going to be very much the same way. Okay, very much the same way. The only thing is, like with trusses, we could pretty much assume that the forces were constant across the members. We can't really do that with moments. Okay? The only other thing that I want to bring about is the idea of a unit conversion. Did we have to do any unit conversions when we calculated truss deflections? Now, some of you are shaking your head no, but I argue the answer to that is yes, okay? But we did it sort of in a subtle manner, okay? Let's take a look at this, okay? So let's recall virtual work for truss displacement, okay? So to compute the displacement of a truss joint, and we're talking about typical USCS units, just typical units. So forces in kips, member lengths in feet, so on and so forth. Okay? So this was the formula that we used, right? That's the same thing I have over here, little f big FL over EA. Okay? And so let's take into account what each of these terms are. Okay? So the big F is the real forces from the real analysis, and the little f is the virtual forces from the virtual analysis, right? Big F is measured in kips, little f is unitless, right? It doesn't have any units, right? Okay, now what about the member length? The member length needs to be expressed in inches, right? Because this is in KSI, this is in square inches, right? Okay, but if I gave you a truss, did I tell you that the truss members were 140 inches long, or did I tell you that the truss members were 10 feet long, 25 feet long, 30 feet long? What did you then do to those truss member lengths? You converted them to inches by doing what?
Multiply by 12.
You multiply them by 12, right? So I propose that we have a conversion factor here of 12, okay? That if we had left everything in feet, our answer would not have made sense if we had not multiplied the answer at the very end by 12 because the member lengths would have had to be in inches. Does that make sense? Is everybody okay with that? Okay. If that's the case, I propose we are going to have similar conversion factors for beams and frames, but they're going to be a little different. So we're going to have a conversion factor for deflections and a conversion factor for rotations. We're going to get to this near the end of our lecture today, but I just wanted to have everything here on the board. So our conversion factor, I'll go ahead and tell you right now, for deflections is going to be 1728. And we'll talk about why it's 1728 here in a bit. And our conversion factor for rotations is going to be 144 times 180 over pi. Okay? And like I said, right now I'm just throwing a bunch of stuff at you. You will see where this stuff comes from here in a second. Okay? All right. Everybody with me so far? Okay. Now, let's go back to our energy discussion that we had brought up when we first started evaluating trusses. We said, okay, we're going to treat truss problems like an energy problem. We're going to say energy going into the system has to equal energy going out. Okay? In other words, the stored energy, the energy that the system has to store under applied loads has to equal the deformations that you get under those loads, right? Sort of like Link with the bow in Zelda, right? Link applies an external force to the bow deforms, right? The further that Link draws the bow, the more energy goes into the arrow, right? Same idea here, right? When you apply loads to a system, it deforms. The more load you apply, the more deformations that you get. And so it's a linear relationship if you assume linear elastic behavior, which for most routine structural analyses we do. Okay? We also did some math tricks, two math tricks. The first math trick is we said the problem with a direct energy comparison is that if you want to find deflections at some point, you don't have a load there. So we'll put a fake load at that point. We'll call it a virtual load. We call that P1 in our analysis. So we'll preload the structure with this fake load, then put the real loads on it. So that was our first math trick. And our second math trick was if all the energies have to equal, then each of the components have to equal one another, and we'll just deal with the easiest one. We'll deal with W2 and U2. Set those two terms equal to one another and recognize that P1 is the fake load that we made up. We'll call that load 1.0 or 1. And by golly gosh gee, we get our deflection equals this. Little f big FL over EA, which was what we were after the whole time. Okay? Does that make sense? This we've already seen before. Okay? Everybody with me on the concepts? Okay. Now, just a side note here, and this is what I was talking about with this point right here. This is what I was talking about right here, is that when we're computing displacements, what we're doing is we're summing up the energy in each member. We're summing up that U2 term in every member. That is the displacements, essentially. So summing up the displacements is the summing of that stored strain energy. That definition, this closed formula right here, this formula, this only works if everything is constant inside that sum. I mean the little f, the big F, the E, the A, all those four terms. Okay? The E and the A, that makes sense. That, for the most part, that's going to be constant, I think, in most practical applications. But if the loads are variable, then that isn't going to be the case. So what's going to happen, let's say if the loads are variable. So if the loads are variable, what we're going to do is instead of having sigma, for example, equals F over A, we're going to have sigma equals some function F over A. Okay? And so we will substitute that in. So sigma, instead of sigma equals E times epsilon, so that's Hooke's law. This is sigma F over A. This is d delta over dx. We will rearrange that, and then we'll integrate that by saying du is going to be the force times the displacement, sum, and we get this. And by the way, just so we're all on the same page, so does this definition still work if these forces are in fact constant? So let's say that we have 0 to L of f over EA dx. What if everything in here is in fact a constant? What if I'm wrong? They're not variable, they're a constant. So we'll factor that out. What's the integral of dx? Everybody remember that? What's the integral of 1? X, right? So we'll have little f, big F over EA, and so that's going to be x evaluated from 0 to L. So little f, big F over EA, L minus 0. So the same thing, right? Same thing that we get right here. So if in fact they are constant, this definition still works. So what I propose to you is that this definition is a more general definition of our stored energy if the loads are variable. Okay? Now they're not variable for trusses, but they are variable for beams and frames. Okay? And why are they variable for beams and frames? Just take a look at the moment diagrams we've been plotting for the past 2 or 3 weeks. They haven't been like this, have they? They've been all over the place. So we're going to have to deal with this. By the way, a lot of the integration that we're talking about is stuff that you can plug and chug in a Casio. So we're not going to have to do any out there e to the x tangent of 1/4 x from 0 to pi over 4. We're not doing anything like that. It's pretty simple stuff. So, sound good? Okay. So what we're going to have to do is we're going to have to see if we can come up with this definition. Okay? And maybe more specifically, like here we have an area. Why do we have an I value? What's going on there? Okay? So we're going to talk about deflections in beams. Okay? And what I'm going to try and get to are sort of 2 facts, which hopefully you all have seen before at some point. If I were to draw this on the board, is this familiar? I hope it is, from Engineering 216, right? And the second thing that we're going to draw is y double prime, or the second derivative of displacement is m over EI. Or in some cases, negative m over EI, depending upon your sign convention. But we're going to get to this here in a bit. Okay. All right. So let's go through some math preliminaries just to make sure that we're all on the same page with math. I don't want some of the math that you're going to see in the slides to be all that confusing. So let's just start real basic. Math 229, Calc 1. So if I have a curve f of x, it is bounded, and I want to look at the area between points A and B, and I want to look at the area under that curve, or compute the area under that curve. I'm going to compute that using the following definite integral, right? Fundamental theorem of calculus says that anti-differentiation and integration are basically the same thing, okay? Now, what I'm going to do here in these slides is, this is kind of a mouthful. We're integrating from x equals a to x equals b of all of this. So I'm probably going to write a lot of integrals like this, where I'm basically saying the integral under the region A of some unit. We'll call that dA. So I'm trying to reduce the amount of notation that you see. Sound good? Okay. So using this notation, what I'm going to do is I'm going to define what are called moments of area. Okay. So area, I propose, is the integral of just dA. When I say dA, what I'm talking about is just a little tiny sliver of area, and then the integral of dA is just summing those little slivers up over a given region. Okay? So here are what I mean by the moments of area. Okay? So if the area is just the integral of dA, then the first moment of area would be the integral of x dA, or the integral of y dA. Okay? Now notice that if you look at my slide here, it looks like that I've got a typo because I'm saying qx is the integral of y dA, and it looks like my symbols are flipped, but they are in fact not. That's actually correct, and here's why. If I have a coordinate system and I have some random arbitrary region in space, okay, and I pick this point right here, okay, how far away is that point from the x-axis? It is some distance y, right? So if you want to talk about how far away you are from the x-axis, it's some distance y. If you want to talk about how far away you are from the y-axis, it's some distance x. So that's why these are flipped, okay? Does that make sense? So a first moment of area would be the integral of x dA or y dA. A second moment of area would be the integral of x squared dA or y squared dA. So you can get the idea. You could have a third moment of area, a fifth moment of area, a 47th moment of area. If you just keep integrating x to the third, x to the fifth, x to the 47th, what have you, right? In mechanics, okay, I propose that for the most part, the first moment of area and the second moment of area are only the ones that have immediate usefulness to us as engineers, okay? The first moment of area is what we would use to locate a centroid, okay? For example, if I integrate y dA and I divide that by the integral of dA, that's sort of like that, right? And isn't that y bar? Remember that? Remember locating centroids? So the first moment of area is useful to us as engineers because we will use that to locate centroids. The second moment of area is useful because it is what's called the moment of inertia. I have a feeling, hopefully everybody's heard of that term, the moment of inertia? Okay, so mathematically the moment of inertia is just the integral of either x squared dA or y squared dA over the region in question. Okay? The reason why I bring it up is because it's going to show up in our derivation. Okay? Now, the other math preliminary I want to talk about is what's called the curvature of a function. Okay? So, if I have a given function, how would I evaluate its slope? Well, I evaluate its slope by calculating the first derivative, right? If the first derivative is related to the slope, what's the second derivative related to? Remember this? Remember the term? The term is concavity. Remember concaved up or concave down? Remember that? Okay. So the slope is related to the first derivative. The concavity is related to the second derivative. What about the curvature? I would bet that if you took Calc 1, there's a chance that you either didn't talk about curvature at all, or if you did, it was a passing, fleeting thought, right? Because I bet nobody even remembers what the curvature formula is. That's the curvature formula, okay? I didn't, like when I was in instructional, and I was like, oh, I don't remember this. I'm sure we talked about it, but it was probably just fleeting, okay? To calculate the curvature of a function, this is how you do it. You take the second derivative divided by all this hullabaloo squared, okay? All this hullabaloo down here raised to the 3½ powers. Now, what I propose is that what we're going to do in this class is we're basically going to say that the first derivative is really small. So if you square it, you get a really, really, really small number. So we're going to approximate this as just that. That's what we're going to do, okay? Because again, we're taking a derivative and squaring it. So we're taking 1 plus a really tiny number. So we're going to basically say that's 1, and 1 raised to any power is 1. So that's how we're doing that, okay? Everybody good? Okay. All right. So far, so good. Okay. So, the mechanics for beam deflection. So now let's get into beam deflection. The mechanics for beam deflection are a tad different than the mechanics for axial deformation, okay? And I'm going to try and illustrate what these mean, okay? We do have some background that's kind of identical. So for example, we are going to assume that behavior is linear. we are going to assume the behavior is elastic. That part isn't really going to be a problem. We don't have any permanent deformations, anything like that. One thing that we are going to have to deal with, though, is this idea right here. We're going to say that deflections are small when compared to the original member lengths. And that's really just a fancy way of saying the following. Okay? When I load a structure, it deforms. I then do not need to go and recheck equilibrium to make sure that the reactions haven't changed or the moment diagram hasn't changed once the structure is deformed. I mean, technically, it's a different structure before and after deformation. But I'm proposing that the deformations are small enough that it doesn't substantively affect our analysis. And so what we are doing is what's called a first order analysis. That is not to say that we don't have second order analyses that we have to conduct in engineering. We do. Often they are related to stability related problems with structures buckling and whatnot. And so they tend to get relegated to more specific like design applications, like there's ways of doing second order analysis in steel design and concrete and so on and so forth. So if you take steel, we'll talk all about that. Okay. Now, if you deform a beam, what we propose is that the neutral axis of that beam remains unstretched, okay? So if you take a beam and you deform it, like if you take your notebook there and bend it, we propose that the center of the beam remains the same length. And so for example, if the beam looks like this, we say above the neutral axis, the beam gets shorter. Below the neutral axis, we say the beam gets longer, okay? So sort of the bottom of the beam stretches, the top of the beam smushes together, okay? So let's see if we can apply some algebra to figure that out, okay? So let's go back to some basic geometry, okay? And so we're sort of treating this like a circular segment. So if rho is the radius and theta is the angle, we can say that the initial length, this unstretched length right here, is just rho times theta. Y'all remember that? Like if you have a circular sector or segment, that the length is just the radius times the angle, right? And that's the initial length. The final length, or the stretched length, as it were, would be the same thing. It would be rho times, or it would be the radius times the angle, but the radius is different. It's not the radius, it's the radius minus however far up we're going. Does that make sense? So the initial length is rho times theta. The final length is rho minus y times theta, that quantity. Okay. Okay. All right. So here's what I'm going to do. Do y'all remember how to compute strain? Do y'all remember strain? Strain was a fraction, like when strain was first defined to you. And wasn't it something like change in length divided by the original length? Y'all remember that? Change in length divided by the original length, and that's how you define strain? So maybe what I'll do then is I'll say, okay, if I want to define strain, I'll say the change in length over the original length, which in this case is going to be L final minus L initial over L initial. So if you're wondering like where I got this term, it's just change in length over the original length. And after doing the algebra and working it out, a lot of stuff cancels, like my rhos or my thetas cancel. I end up having some rhos cancel, and I end up with negative y over rho. Okay? So far so good? Okay. All right. So that's strain. Okay? So if I wanted, I could take strain times E and get stress. So far so good? Okay. So what I'm proposing is I have one equation for stress. So one equation for stress is EY over rho negative. And then the next thing I'm going to do is I'm going to see if I can get another equation for stress, I'm going to see if I can set those two equal to one another. Okay? All right. Has everybody got all this? Let me stick here for a second. Now this is good if y'all ready. I'm not going to get in your way. Everybody good? Okay. So now let's see if we can look at this another way. Let's see if we can look at this from an equilibrium standpoint. So this first derivation was sort of like, okay, let's take a look at the structure deformed and get back to the stresses. Whereas this derivation, I'm going to look at the forces in the equilibrium and go that way and see if I can make them match. So like I said, I propose that the center of the beam doesn't deform. Well, if the center of the beam doesn't deform, then I propose the center of the beam doesn't have any stress. Okay? And I propose that stress linearly varies from the centroid. Okay? At the centroid, we have no stress. As we get below the centroid, the beam stretches, so I have tensile stress. As we get above the centroid, the beam squishes, so I have compressive stress. Right? So how would I start attacking equilibrium? Well, maybe what I'll do is I'll take a little tiny element at some random point, doesn't really matter. Let's take a little element right here, and let's say it's got some stress, and the area is some little sliver dA. Okay? So I'll say that the force in that element is sigma dA. Okay? Now the moment arm from the neutral axis is some distance y. So if I take sigma dA, multiply it by y, and then integrate all that, that'll give me the moment. Okay? Now I'm throwing a negative sign in here just to result from our sign convention, like smiley face positive. So our stresses are, opposite sign convention. Like up here, this is a positive distance, but that's a compressive stress, so it's negative. So that's why the negative comes from. So now what I've got is I've got this m sigma dA, or integral of, sorry, m is the integral of negative sigma y dA. What's sigma? Sigma's that. So I'll take that sigma, plug it into here, and I get that. Anything look familiar in this equation? What is the integral of y squared dA? That's the moment of inertia, right? So I'm going to take this and replace it with just the moment of inertia. And so I get m equals EI over rho. And rho in this case is the radius of curvature. Okay? So we're sort of getting to this real quickly. So I've got that our moment is EI over rho. So I can rewrite that as curvature, because if rho is the radius of curvature, 1 over that is the curvature, m over EI. And we said that we were going to approximate curvature as the second derivative. And then we get to this, that the second derivative of deflection is m over EI. This is one of the most fundamental equations in all of mechanics. Okay? Now how do you get to this? Well, if we were in Engineering 216, basically all we would do is we would say, okay, here's our stress profile. That distance is y, and then the slope of that line is just m over I. So that's how we would get to that. But in here, we don't really care so much about this equation as we do about this one. And this is, again, as I proposed, it's like one of the most fundamental equations in all of mechanics. Okay? That is our, so if you ever hear the term moment curvature, this is what we're talking about. If you ever hear the term Bernoulli beam bending equation, this is what we're talking about. I said Bernoulli, and you said, this is not fluids. You're not allowed to mention that word in here. So,
this is a safe space.
This is a safe space. This is a laminar space. I need to stop talking. I need to stop talking about fluids, right? I'm sensing some turbulence in the crowd.
No, the jokes are really flowing.
That was good. That was really good. All right, I'm done. Okay. I love my job. Okay, so now I want to see if I can use this equation to get to this, to get to our method of virtual work. Can we apply the method of virtual work for deflections and beams and frames? Absolutely. Okay? So let me show you how it works. So how does virtual work change for beams? Okay? So first off, in the method of virtual work, remember that we analyze two structures. We analyze the original structure with all the loads present, and then we analyze the virtual structure with a single unit load at the point of interest. Okay? That is still the same for beams and frames. Nothing changes. Okay? But what does change is maybe our definitions for what these W and U terms are, because the mechanics are different. Okay? So one thing I'll point out is that when we start doing virtual work for beams and frames, not only will we be interested in how much a point deforms, but we'll also be interested in how much a point rotates. Okay? So there's a difference between a translation and a rotation, or a deflection and a slope. Okay? So what we'll do is that if we're interested in how much a beam deforms, we'll just put a unit deformation. If we're interested in how much it rotates, we'll put a unit moment. And just to sort of make the point of what I'm talking about here, I'm talking about, here's a beam, and let's put some loads on it, okay? When the beam deforms, it's going to deform maybe something like that, like that's what it's going to look like when it deforms. So maybe we'll be interested in the displacement, but we'll also be interested in that angle change, okay? So we're going to get both. We didn't really get that with trusses. With trusses, it was just really a displacement at the joints. With beams and frames, we could get both. So we might be interested in how much this rotates or how much this deforms. And so we just handle it with a unit force or a unit moment, okay? And just like with truss deflections, we assume a direction. If it's positive, our assumption's correct. Otherwise, we just flip the direction of our answer. So what we're going to do is we're going to use this to find U2. So we're going to integrate. So we take our second derivative of displacement, which is m over EI. If the second derivative of displacement is m over EI, then the first derivative of slope is m over EI. So I'm just saying slope is the derivative of the displacement, okay? And so we have to integrate because moment changes as a function of x. This is really the big reason why we can't use this, but we have to leave things in integral form, okay? We're going to handle this the same way that we handled the derivation for truss members. If the force changed, we're going to handle it the same way. So what we're going to have is a little change in angle is m over EI dx, and we're going to leave that as a function. Then what do we do here? Our internal energy is just a little virtual force times a rotation, not a displacement in this case, a rotation. And so leave that in functional form, leave that in functional form over EI dx, and then just integrate. Set the two equal to one another, and again, we can let that virtual load be whatever we want, so we let it equal 1, and then we get this. So again, the big difference between a truss analysis and a beam analysis or a frame analysis in terms of deflections is that we have to leave these in function form because moment diagrams go up and down and up and down and up and down, okay? All right, so here's virtual work for beam deflections. So this works regardless of whether or not you're trying to find a translation or a rotation. It doesn't matter, same process. We take our moment functions and integrate them. So we're going to have two sets of moment functions. Don't worry, we're going to have a lot of problems on investigating how to do this. We're going to have moment functions from real loads, and we're going to have moment functions from virtual loads. So we're going to have, instead of a little f and a big F, we're going to have a little m and a big M. Instead of them being numbers, they're going to be equations. So like little m might be x plus 3, and big M might be x squared minus 4, right? And so we're going to integrate them. But when I say integrate them, what I'll say is our Casios can do a lot of the work for us. So we'll be able to employ that. So if you have a calculator that can do integration, you probably won't have to actually do any Calc 1 in here. So, but don't worry, we'll have some practice on this. We'll have our E value in KSI. We'll have our moment of inertia in inches to the fourth, okay? And as we're gonna see, the actual integration itself is actually gonna be pretty easy. The hard part is actually what's in this box right here. This is the part right here that's gonna drive you all up the wall, is that if you have multiple moment functions, you're gonna have to perform multiple intervals, okay? In fact, all the example problems that we're gonna do together are gonna be just about this. That's gonna be the problem, okay? So don't worry, that's really sort of the main thing that we're gonna be investigating. Okay, one thing left to discuss before we call it today are dimensional considerations. And let me go back one just to sort of make the point. We do have a dimensional mismatch in what I have here on this slide, because I've got moments in foot kips, but I've got this in KSI, and this is inches to the fourth, right? So there's something wrong in the dimensions, and I gotta sort that out, okay? So I wanna talk about these dimensional considerations, but I kinda wanna talk about them generally. So I just wanna make like a point about something, okay? So bear with me. This is just, you know, for almost like a thought experiment, okay? So if I integrate x squared dx, right? What is the integral of x squared dx?
X cubed over 3.
X cubed over 3. Okay. Plus c. Thank you. You're 100% right. Okay. Let me ask this question a little more generally. Okay. What would the integral of this be? Okay. Now, let me sort of ask you what I'm asking. What is the highest order x term in this equation? X squared, right? It's a 2. When I evaluate the integral, I get a higher order term that's going to be a higher order of 3, right? Whenever I integrate, I go up in order, right? Everybody with me on that? Okay. So before we get to this, let's just sort of take a step back, okay? So my second derivative of deflection is m over EI. The second derivative is m over EI. From a units perspective, it would be, you know, foot kips divided by EI. If I integrate one level up, from a units perspective, I'm going to have another length unit, right? Sort of like if I have an integral that's highest term is x to the third, and I integrate, I get another x term, another x to the fourth, right? So from a units perspective, I'm 1 up. Does that make sense? So if I integrate again, I'm going to be yet 1 more up, right? So units perspective, theta is going to be in units ml over EI, deflection is going to be ml squared over EI. So far so good? So let's start plugging in units and seeing what happens. So if let's see, forces tend to be in kips, length tends to be in foot, so distributed loads would be in foot kips, distributed loads would be in kips per foot, moments would be in foot kips, E would be in KSI, moments of inertia would be in inches to the fourth, okay? So if I start plugging this in, what happens is I get foot kips times foot, kips per inches squared, inches to the fourth. Do all the algebra and I get foot squared over inches squared. This is what rotation gives me. And if I do the same thing for deflections, I'm going to get foot cubed over inches squared, okay? So I've got foot squared over inches squared, foot cubed over inches squared. How do I correct that? What I need to do is I need to figure out what do I want the answer to be, okay? Here, we needed a conversion factor of 12. Why am I coming up with 1728 and 144? Well, I'm coming up with 1728 and 144 because I'm going off of my desired units. I want probably slopes and rotations to be in degrees. Maybe I want my displacements and deflections to be in inches. So what I'll do, for example, for rotations, is I'll say I've got foot squared over inches squared. So what I'm going to do is convert this foot, 12 inches per foot, but then do it again because it's foot squared. So 12 inches per foot, 12 inches per foot, and then if all I did was that, then the answer would be in radians. If I want degrees, do 180 over pi. So what do I get for a conversion factor for rotations? I get 144 times 180 over pi. What about USCS units? Well, with USCS units, I've got foot cubed. So I convert 12 inches to foot, 12 inches per foot, 12 inches per foot. 12 times 12 is 144. 144 times 12 is 1728. See, this is just 12 cubed. This is 12 squared. I'm adding a 180 over pi to get it into degrees. Okay, that's why that is. Okay, so today was all about, here's a bunch of info. I'm throwing it at you. Wednesday, Friday, so on and so forth, we're going to start using this info. Okay? So, these are going to be the unit conversions that we're going to start using on Wednesday. Again, this is one of the reasons I didn't give you any homework today. I knew I was going to throw a lot at you, so I wanted to just sort of let it sink. All right? Sound good? All right, I'm letting you out right at 10:50. I'm going to pull up the code one more time. I will see you all on Wednesday.